In this video, I will talk about the necessary theory that we need to use when we solve the differential equation with an ideal spring force, a resistive force, and a force that drives the oscillation. This is a differential equation that we get in this case. This is the acceleration that we get from Newton's second law. The minus bx dot is part of the resistive force, and beta is the parameter that we use. Omega naught squared times x. This term comes from the ideal spring force, and the lowercase f as a function of time. This is the force that will drive the oscillation. Just to give you an idea, if you can visualize, you have a person, a child on a swing, and you have a parent, a sibling behind the swing, exerting a force on the swing periodically. This would be an example of this driving force. Now, it does make things a little bit easier if we introduce a differential operator, the uppercase D. If I define D to be this, then it makes my life easier to write the left hand side, because to get the left side, the only thing I need is to take this operator and apply it to x. So when I say, if this is the definition, dx will give me the second derivative of x as a function of time, the first derivative of x as a function of time, and then omega naught squared times x. Now, using this definition for a differential operator, I can rewrite this expression as dx equals the right side, the driving force. Now, some terms here. If I have a differential equation like the ones I solved in the previous case, where dx equals 0, this is a homogeneous differential equation. And just so that I can move on with the theory, I will write the solution to this homogeneous differential equation as x with the subscript h, to denote that this is the solution to the homogeneous equation. Now, on the other hand, if I have dx equals the driving force, this is what we call an inhomogeneous differential equation, and I will use x sub p, where p stands for the word particular. This will be the solution to this differential equation. Now, first, I want to mention, before I move on with the important part, I do want to show you some ways that I can use this differential operator. So if, let's say that x1 is a solution to the differential equation, then what this means is that if you take the operator D and you apply it to x1, you will get a 0. Now, if I have A times x1, this is what's going to happen. I'm going to take the operator D and I will apply it to A times x1. Now, when I do that, I will be able to take the constant A out of the operator, and then I will have A times dx1, and this will give me 0 because dx1 is 0. Also, if you have something more complicated, ax1 plus bx2, then you can do something similar. ax1 plus bx2, this will give me d ax1 plus d bx2, and then I can do a times dx1 plus b dx2. And then because this goes to 0 and this goes to 0, you end up getting 0, which means ax1 plus bx2 is also a solution to this differential equation. Okay, this is just a quick introduction to how you can use the differential operator to make your life a little bit easier. All right, now I'm going back to what I was saying before. Since x sub h is a solution to the differential equation, then this means that dxh is 0 because x sub h is the solution to the homogeneous equation. And because x sub p is the solution to the inhomogeneous differential equation, I have this to be true. Now, I want to see what happens when I use the sum of those two, x sub h and x sub p. So, as before, this will be now, as I said, I know that dx sub h will give me a 0, and the other term will give me the driving force. So this is equal to the driving force. This is telling me that the solution, that is the sum of those two, is a solution to the inhomogeneous differential equation, the one that I'm trying to solve. Now, here is the thing. What's the difference between the sum and simply x sub p? Because I did mention that this particular solution, the x sub p, is a solution to the differential equation. What is the difference between the two? Well, I want to remind you, when I solve the homogeneous solution, the homogeneous differential equation, here this will include the two parameters, the two constants. In contrast, this particular solution will include 0 parameters. So, can I claim that this is the general solution to the inhomogeneous equation? No, it is not. This is a second order differential equation. Okay, so this is a second order differential equation. Practically, that means my general solution will need to have two parameters. So, if I found a solution, a single solution to the inhomogeneous differential equation that has 0 parameters, it is fine. I found a solution, but it has 0 parameters, which means this cannot possibly be the general solution to the differential equation. On the other hand, I do have a solution to the homogeneous differential equation that has 2 parameters. And I just showed that the sum of the two is also a solution to the inhomogeneous differential equation, and it has 2 parameters. This allows me to conclude that this is the general solution to the inhomogeneous differential equation. Okay, so what I will be doing to solve my differential equation, the one that I get from driven damped harmonic motion, what I'm going to do, the first thing I'm going to do is solve the homogeneous differential equation, and this will give me this solution. I will try to make a guess and find a particular solution to the inhomogeneous differential equation, and then I will simply add the two, and that will be the general solution to the inhomogeneous